In this lecture, we're going to start looking at supervised learning. We're going to look first at some basic concepts to have a general idea of what supervised learning is, and look at two different types of problems, regression and classification. And then we're going to look into more details on how we can find an hypothesis to solve a supervised learning problem in the case of regression, and we're going to fit curves to data points with least mean squares. So the basic concepts here are that we have a set of data, of examples, for which we also have some target value. So the notation here means that each example has this x-y pair. The x can be a vector of a number of features. For example, if these are houses, it can be the location, the size of the house, the age of the house, the number of rooms, and so on. And this would be the target value that we want to predict. We want to predict, for example, the sales price of the house. So we would have in our data set a set of houses with all of their features, and for each house, what would be the correct sales price. For example, we could gather this data from houses that were previously sold. And now we assume that there is some relation between the features and the value we want to predict. So it's as if somewhere in the universe there is this function, we do not know the function, but it exists, that allows us to map between the features of the houses and the sales price of the house, or in general, between the features and the target value that we have. The goal of supervised learning would be to find an approximation of this function by choosing from a set of hypotheses. So we have a hypothesis class. We have this model, this g function that has these parameters that allows us to choose hypotheses from this hypothesis class. And by selecting these parameters, we can get an approximation to this f function so that we can also map from the features that we have to the value that we're going to predict. And this is supervised learning because since we have the target values for all our examples, we can check during our search for the best hypothesis. As we change these parameters, we can keep checking if our predictions match the values that we want. So we can try to do this in order to approximate as well as possible the predictions to the target values. So ideally, we would want to parameterize our model, to find the hypothesis that approximates the target values for all possible examples in the universe. But now we're only going to consider a sub case of this problem, which is looking only at our training set. So the training set is the set of data that we are using to adjust the parameters and select the best hypothesis. More generally, even if we don't have a model with specific parameters, the training set will always be the data we use to select a hypothesis. The training error is the error that we can measure on the training set. So as we are looking at different hypotheses, we can always compare the predictions from the hypothesis to the target values that we have in the training set and measure the error. So the error measured on the training set is the training error, or in some older literature, you can also see it referred to as the empirical error. So for now, we're going to try to predict the target values, the y values in our training set. We're going to measure the performance by looking at the training error. So as the smaller the training error is, the better the performance of our hypothesis. And the data that we have for training is this set of examples. Each x can be one value or it can be a vector. In our simple examples, it will be just one value, but you can have a vector of features. And we have this target value for each example that we want to predict. Now, in supervised learning, we can find two different types of problems. In a classification problem, what we want to predict is a discrete class label. There is a fixed number of classes, and so we want to find a function that partitions our data into these different classes. One example would be try to detect spam emails, or try to predict from the characteristics of a mushroom if it's edible or poisonous. So in these cases, we would be partitioning our data into the different categories. In a regression problem, we are trying to predict a continuous value. So we are trying to approximate some function that fits as best as possible our predictions to those values. So basically, we're trying to get our predictions to be as close as possible to the values that we have there. And this can be for predicting trends, prices, anything that is continuous. So we're going to look at regression problems first. These are simple to illustrate. And we're going to consider a linear regression. So it's actually a polynomial fitting. We're going to fit a polynomial curve to a set of data points, but I'm going to explain why this is a linear regression. And we're going to start with what intuitively we can imagine when we consider a linear regression, which is trying to fit a straight line to a set of points. So our hypothesis class will be the set of straight lines. Our model will be this. This can describe our hypothesis class. And we have two parameters here. This theta1 determines the slope of the line because it's what we multiply by the input, by the x value. And theta2 is a constant that determines if the line is more up or down on the y-axis. So this would be our model. By adjusting these parameters, we can select different straight lines, different hypotheses, and now we want to find the best hypothesis from our hypothesis class. The hypothesis class would be all the straight lines that we can write using that model, and we need to figure out which is the best one. Our data will be this set of points here in red. For each point, we have the x value, the feature, and also the target value, the y coordinate there. So we want to find the line that best allows us to predict the y value of each point from the x value given. So the question now is how can we find the best line? How can we create a performance measure here that will allow us to decide which of these hypotheses is the best one? So let's assume that our data results from some unknown function that corresponds x to y. So there is something in the universe that makes these values of x have lower y and these values of x have a higher y. But there's also some noise here, because when we are measuring these values, our instruments may not be 100% accurate, so we have some random error here. And we're going to assume that this random error is normally distributed. So as that Gaussian curve, that bell-shaped curve. So what we can do here is, if our function, so if the line that we chose here by setting the parameters is close to f, then we can consider the probabilities of having this kind of data because of the error that we have associated with each point. Or more generally, we can simply assume this is the correct function, and now the probabilities are given by the deviation from the predicted value that we have, that we can assume it's because of this random error. And since we know the distribution of the random error, Gaussian, we can compute these probabilities. So basically what we're saying is that if this black line is correct, then the reason why this point is not on the line is because of that normally distributed random error, and we can estimate the probabilities of, or try to minimize the probabilities of this point being this far away from the line. So this basically, this is the relation between the joint probability distribution of two variables and the conditional probability. The conditional probability of y given x is given by our function and the random error. This is basically what relates x to y, but with this f replaced by the function that we are finding. So each hypothesis that we are considering. This we can relate this by multiplying by the marginal probability of x to the joint distribution of the two variables. Now, the reason why this is interesting is because intuitively we may think that we want to find the hypothesis that maximizes the probability of the data being as it is. So if we go back here, for example, this green line makes the points being very far away. And if that noise is normally distributed, these will have a very low probability because they are far from the line. On the other hand, this black line makes the points all closer to the line than what happens with the green line. So we may say that the black line is better in the sense that if the black line is correct, the points have a greater probability of being distributed like this than they would have if the green line was the correct one. Okay, so this is the notion of likelihood. Basically, the likelihood of the parameters that we have, or the hypothesis that we are choosing, is the probability of the data, assuming that this is the correct hypothesis. This seems a bit twisted around, so in reverse, but it's necessary to think of it in this way, because the data points that we have, we can consider them to be a random sample from the universe. This is the set of houses that we randomly chose and measured the total area, the number of rooms, and so on. But the parameters that we are adjusting in our function, in our model, are not random variables. They are either correct or they are not correct, but they are not a random sample that we are obtaining. So under this reasoning, we cannot really talk about the probability of the parameters. That would not make sense because it's not a random variable. But we can talk about what the probability of the data would be if the parameters are correct. And this can be given by this assumption that we know what the noise is like, what the error is like. So this would be our approach. We're going to try to maximize the likelihood. That is, we're going to try to maximize the probability of the data being as it is under the assumption that we have the correct hypothesis. And so now we're going to change the different hypotheses and see which one gives us the largest probability here. So one trick to do this, so we can do away with all these multiplications, is to use the logarithm. The reason for this is that if we have a set of n points, in order to compute the probability of all the points being like they are, we must multiply the probability of the first point having that value and the second point having that value, and so on. So this gives us these large products that we can do away with the logarithm, converting them to sums. We can also ignore this term here, because even though the likelihood is the probability, the joint probability of the two values, and this is the product of the conditional probability and the marginal probability of the features, we can ignore this part, because what we want is to find the parameters of our function that maximize the likelihood, and this term does not depend on the parameters of our function. This is merely the probability of finding houses with those particular features or examples with those particular features. What depends on the parameters is this estimated probability of y being some value if x has that particular vector, because this is what is coming from our function here. We have this function trying to predict the values of y. So we can simplify that. The likelihood, the logarithm of the likelihood will be proportional to this. And now if we replace here the expression for the normal distribution, because we are assuming that this noise, which gives us the probability of the points having those values around the predicted line, we assume that this is normally distributed. So replacing there, we have this expression, simplifying with the logarithm and removing the constants, because remembering we are trying to maximize this expression, so all the constants we can ignore them, and we end up with this expression here. So the logarithm of the likelihood of our parameters, the parameters that specify the line for this data set, is proportional to minus the sum of the squared differences between each target value and the corresponding prediction we are getting from our model. So if we put this the other way around, we can do away with this sign, and instead of maximizing, we can minimize. We can think of this as minimizing the quadratic error. So we are minimizing the sum of the squares of the difference between our predictions and the target values. So this is a very common way to approach these kinds of problems. When we assume that the error is normally distributed and is affecting only the target value, then maximum likelihood solution boils down to minimizing the sum of the quadratic errors. This is why this sum of the quadratic errors is often used as a measure of performance. But note that this only makes sense because of our assumptions, which is that we are approximating some function that predicts the value that we want to predict, but affected with some noise that has a normal distribution. So if the error is only affecting the prediction and is normally distributed, then the parameters that make the data as probable as possible, if assuming that the hypothesis is correct, will be the parameters that minimize the quadratic error between the predictions here and the labels that we have, so the values that we have in our training set. Sometimes you will see the squared error written with this constant here, but this is usually just a convenient constant so that it compensates the 2 there when we compute the derivative. But if you see this in the literature, don't worry, it's the same thing as this because we are trying to minimize. It doesn't matter if we have that constant there or not. Okay, so let's do this least mean squares minimization to try to find the best line. So what we want to do here is to adjust those two parameters, the parameter that determines the position of the line here and the parameter that determines the slope of the line, in order to minimize the sum of the squares of all these differences between each point and the corresponding prediction in the line. So we find the parameters in this way, minimize the quadratic error, and we can visualize this expression as a function of these two parameters as a surface like this. So this would be one of the parameter, this would be the other parameter, and if we move away from the ideal combination, we have a very high quadratic error in total. If we go down this surface, then we reduce the sum of the quadratic errors and we approach the ideal set of values for the parameters, so we approach the best hypothesis in our hypothesis space. And this can be solved with numerical methods that basically look at the derivative at some point, slide down the derivative that way until they reach a minimum in that direction, and then compute again the derivative, slide down until they find another minimum, and so on until they converge to an optimal solution or close to an optimum solution. Since this is a quadratic surface, it has this nice behavior, this nice shape, and makes it easy to find the best spot. So doing this with our model with a straight line, so considering the hypothesis class as the set of all straight lines, we can choose the best straight line to fit our data. And we can see that this is not a very good model. So if this is the best hypothesis that we have, our model is not very good because it cannot really go with the shape of this data set. We are trying to fit something that is clearly curved with only straight lines. So what we can do here is to change the model. Instead of using a straight line, we can start curving. Now, why is this still linear regression? We can imagine that what we are doing first is changing the data. Instead of having only x and y, we're going to have two values for x. So now we're going to increase the dimensions of our problem, where this first coordinate is the square of the original x, and the second coordinate is simply a copy of the original x. So we are not creating new information here, we are simply taking the original x and also adding the square of that value as a new dimension. So because we are using a nonlinear transformation, and this is important, this square is a nonlinear transformation, what we get is that in these two dimensions where we have the original x and the x squared, our data is now all, the x values for our data are now all in this curve here. So if we plot this set of points that we have here, just the x and the y, but we plot them in this space where we have x and x squared and then y in the vertical direction. We have these points here, but they are in a curved surface. So this is like the part of a barrel, and it curves like this. So now we can do a linear fit here. We can do a linear fit in 3 dimensions. It's just the same thing as the line, but in this case, this is a plane. We have one slope for each coordinate plus one constant. And this will give us, when we fit with the least mean squares, will give us this plane that is the best fit to these points here. But since these points are now distributed in a curved surface, because we used the original coordinate and the square, if we compute the intersection of this plane with this curve here, so projecting back to the original space, we have something that is a curve. So the idea here, and this is an important idea that we're going to see many times later on, is that we are still using a linear model. We are using a plane in 3 dimensions. That is a linear model. But because we did a nonlinear transformation of our data, when we get back to the original space where our initial data was, just the x and the y, the result is a curve when we fit the model to the data. So actually doing these kind of transformations, even though our hypothesis space is the set of planes in 3 dimensions, it becomes a set of curves in 2 dimensions when we project it back using this nonlinear transformation. So this would be the result. It's the equivalent of fitting our data with a polynomial curve of degree 2, because if you recall, this coordinate here is actually just x squared. So we did this transformation here. So actually what we have here is a polynomial of degree 2, where we have theta 1 multiplied by x squared, theta 2 multiplied by x, and then a constant. It's the same thing, but we can think of it as a linear model in 3 dimensions and then project it back by that nonlinear transformation. So now we can do this easily with polynomial fit. So I'll just show you the code. Here we're going to use these libraries. NumPy makes it easy to do this kind of operations with matrices and vectors and so on. Matplotlib we're going to use for plotting. This polydata CSV file is the file where I have the coordinates for these red points. And when we load with NumPy, this gives us a matrix. So the first column is the x value. I'm going to put the first column of the matrix in the x value. This notation indicates all rows and the column of index 0, which is the first one. Remember that in Python, indexing starts at 0. The y values are on the second column. So from the matrix, we have all the rows and column of index 1. And now we can fit a polynomial of degree 2 using these x and y values. And this we can do by using polyfit. Polyfit will do a least mean squares fit between the polynomial and the target values that we have here. And this gives us the coefficients for the polynomial. Now to draw this line, we need a large number of points so that we don't see little elbows in the plot. So this looks like a smooth line. One easy way of doing that is to use this linspace function that gives us this number of points, in this case 100, uniformly distributed between the minimum and the maximum here. So between 0 and the maximum value of x. And now we compute the y values for the polynomial by simply using these coefficients applied to these values of x. So we are creating 100 points here distributed in this axis and then computing the y value for the curve for each of these points. And now this is simply plotting. We create a figure, we draw the data with red circles. This is O for a circle and R is red for the color. Then we draw the polynomial curve with a line, and this is just to put the scale of the axis, the title, and save the figure to a file. So this is the kind of things that you can do if you want to experiment with different, you can experiment with different degrees, simply changing here the values. So degree 3, degree 6, whatever you want. and use this code to experiment here. And that's what we can do here. This would be the second degree polynomial. It's still not very good because the data seems to go down and up again, and the second degree polynomial doesn't quite match that. But we could use this to go a bit farther. So the idea here is that we are adding dimensions with a nonlinear transformation, and then we are using a linear model in this higher dimensional space. In this example, we went from 2 dimensions, which was x and y, where we have just a line, and then we go to 3 dimensions by adding the x square as a new coordinate for the features and using a plane as our linear model. In all of these cases, we need to assume something about the hypothesis. So this is what gives us the inductive bias, and we'll see that this is important for generalization, for going beyond the data that we have and to predict new values. But note that if we assume that we have a straight line in 2 dimensions, we have a more restrictive hypothesis class than if we have this plane in 3 dimensions after the expansion, or the equivalent, which is a second degree polynomial. Or if we use a third degree polynomial, we are increasing the hypothesis class and so on. So we can adjust this with different polynomials, different hypothesis classes, but we have to be careful, as I'm going to show in just a few minutes, that if we increase too much the power of our hypothesis class, we are reducing our inductive bias, and so we may lose the ability to generalize. So let's look at that problem here in this example. If we use a polynomial of degree 3, it seems to give us a better result even than 2, because now we have everything going smoothly close to the points that we have. So this would be the equivalent of expanding our data into 4 dimensions by adding these additional 2 coordinates, x squared and x cubed, and then doing a linear model, a linear hyperplane in those 4 dimensions. But we can also imagine this as just fitting the degree 3 polynomial. We can increase the degree easily. This would be degree 5. This would be, for example, degree 15. And now we can see that even though with a polynomial of degree 15, we can get very close to nearly all the points. So this seems to be much better than the degree 3 polynomial to predict these particular points that we have in the training set. And this is the measure of performance that we've been using to fit our data. But we can get a bit suspicious when we find something like this. Intuitively, it seems wrong that between these 2 points, we would have a prediction that is so far away from the points themselves. Of course, at the position of these points, the prediction seems to be spot on top of the points. But where we do not have data, the prediction seems to be running wildly away from the general trend of the curve. So this is what happens when we start reducing our inductive bias. We can improve the adjustment to the data that we are using, to the training set, but we start getting things that may not make much sense outside the training set. And that is the notion here of overfitting. We're going to see this better in the next week, in the next lecture. But the idea is that when we start to adjust our hypothesis too much to the data, so for example, if we have a hypothesis class that is too powerful, includes too many hypotheses with too many degrees of freedom, then we can make the training error very small, but this may increase the error outside the training set. We need some way of preventing this from happening. So we must be able to look outside the training set to figure out when we are overfitting, when we are adjusting too much to the training set. And this is what we're going to see in the next lecture. So to sum up for today, we saw these basic ideas of supervised learning, 2 different types of problems. In classification, we want to partition our data into different categories. In regression, we want to approximate some value, some continuous value that we're trying to predict. And we saw also this important idea of using linear models in higher dimensions after nonlinear transformations to improve the power of our models. So if we just use a straight line, a linear model in 2 dimensions, we are very restricted and cannot accompany the data well in this example that we saw. If we increase to 3 dimensions using a quadratic, that square of the x, so some nonlinear transformation, we gain a bit more power. And as we keep increasing that, doing these nonlinear transformations to higher dimensions, even though we are always using linear models in those corresponding spaces, we keep increasing the power of our model, so increasing the versatility of our hypothesis class, eventually falling into overfitting, where we have so much flexibility that we start adjusting too much to the data and we start getting results that are not sensible outside the points that we have. So we're going to see how to prevent that in the next lecture. In the meantime, I recommend that you read these chapters, chapter 1 of Bishop, and these sections of Alpidens and Marsland's book, which are about this first part for fitting these models.